In this lesson, I'm going to go over a bunch of stuff about how to help us find zeros of polynomial functions. There's a lot of different theorems that you'll hear me use and try to explain. It's going to take some time, but all of these you're going to see are going to be integral to figuring out how to find the zeros or roots of a polynomial function. All right, so one thing that we have already talked about, we'll continue talking about in these lessons, is that if you look at the highest exponent or the degree, that is how many roots or zeros you can expect your function to have. So in this case, this quick example here, we have a power of 2. So I'm expecting there to be 2 roots or zeros in this function. So if I set it equal to 0 and move the 16 over with subtraction, now you probably are noticing something interesting is happening here. When I take the square root of a negative 16, I get plus or minus 4i. So that means one of our roots is positive 4i and the other is negative 4i. Now neither of those roots are real numbers, right? So yes, we do have 2 roots, but this in fact means that these 2 are called complex roots, okay? Now this shouldn't surprise you, because complex roots do not, it means that you're not going to have x-intercepts. So we kind of talked about this at the very end of the first semester. You can have solutions to a function or to an equation, but they don't necessarily have to be x-intercepts. A lot of times they'll be the same, but in this case, these imaginary or complex roots are not actually going to be intercepts. Because if you were to graph this, right, your y-intercept of 16, right, this is the quadratic, what it looks like. You'll notice that quadratic is never going to intersect with the x-axis. So that's how you have solutions, but not necessarily x-intercepts. Okay, let's do another theorem. Now this is great for you guys to see now, especially before a couple years away from calculus. You're going to see this definitely in calculus. This is called the intermediate value theorem. And what this states is that if you have a continuous function and you have, when you plug in 2 different x values, if one of those x values spits out a positive y value and the other x value you plug in spits out a negative y value, at some point, if it's continuous, it's going to have to cross the x-axis to get from one y value to the next. So you can see here, this y value is positive, crossing the x-axis down to get to a negative y value. So if you know the function is continuous, then you can use this, all right? So let's go ahead and do this with this g of x function, which is a cubic function. It is continuous, all right? And we're looking to see the intervals on which this polynomial must have x-intercepts. Now again, it doesn't tell me, find the x-intercepts. Just figure out what intervals do you expect to find those x-intercepts. So here we go. So I'm looking at the y values here. I notice this y value to this y value changes sign. So going from a negative to a positive means on that interval, -2 to -1, there is some x value where the function has to be equal to 0. All right, go to the next ones. The next one has a +1 and a -1. Let me back up just for 1 second. If I were to highlight this 3 and this 1, you should notice that those y values are both positive, so not necessarily going to, or not, not going to cross, doesn't have to cross the x-axis. Now back to the 1 and the -1. Those do change signs. So my next interval is going to be 0 to 1, and that's where I expect to find another x-intercept. And finally, when I look at these last 2 together, -1 and 3, those are also opposite signs. So from 1 to 2. So on those intervals, right? So I expect to find x-intercepts on those intervals because the y values are opposite signs. Now again, this is assuming, right, that we have a continuous polynomial function. All right, this is a cubic function, so it is continuous, right? If I were to sketch it, it looks something like this. Again, I'm just, spitballing here, but it'd be something like that, which is continuous. Okay, let's do the same type of thing on this example here, but instead of finding or figuring out where you're going to have values that are going to be x-intercepts. Now they're saying, okay, is there a value for c, or which is another letter to use for x, right? Is there a number we could plug into this function that's going to spit out and get 1 on this interval 0 to 5? So what I'm going to do is I'm going to plug in 0, then I'm going to plug in 5. I'm going to look at those two y values after I plug them in. If the y value of 1 is in between those, and this is a continuous function, which it is, then at some point there is some value c for x that when you plug it in to your function would give 1. Okay? So I'm going to plug in 0, and I'm going to plug in 5. So that's going to be quicker, right? This one's a little bit simpler because 0 squared is 0, plus 0 is 0, so minus 1. So plugging in 0 gives me negative 1. Plugging in 5 will take a little bit longer, which is 25 plus 5 minus 1, which is going to be 29. All right, now looking at those two y values, I see a negative 1 to 29. This y value of positive 1 is between negative 1 and 29. So because this quadratic function is continuous, right, at some point between 0 and 5, there is some value c for x that is going to make this function equal positive 1, right? That is the intermediate value theorem applied, okay? So again, you're analyzing this y value and this y value, and we notice positive 1 is between negative 1 and 29, and this function f of x is continuous. So that is how we are saying with the intermediate value theorem, there is a value c for x that would make this function become 1 on the interval 0 to 5. Okay, another theorem. This is called the rational root theorem or the rational zero theorem. Essentially, when you are asked to find the zeros or roots of a polynomial that has a very high degree, so like usually with squared, you're hoping, like a quadratic, you're hoping to be able to factor, even cubic functions, you're hoping to be able to factor. But as you get into the fourth power, fifth power, even higher, and sometimes with cubics, you're not able to factor. So what this does is instead of just allowing you to pick any number you want and just plug it in, which you totally can, this rational root theorem will help you organize into the possible rational roots that you're going to test out. So essentially, it kind of just helps refine. Instead of just picking whatever number you want, say, okay, you know, that's a lot. Here's still a lot, but a lot less than infinite numbers to choose from. Let's choose one of these and see if that is actually a root, okay? To do this, you need to look at the constant. So look at the constant term and the leading coefficient. And we're going to write down all of the factors of those numbers. So I think it's easiest to explain in an example. So I'm going to start with the constant, and it doesn't matter if it's positive or negative, all right? This is negative 6 or 6, it really doesn't matter. So you want to write down the factors of 6, okay? So like 1 times 6, 2 times 3. You don't need to write 3 times 2 or 6 times 1. So in order with plus or minuses, you're going to plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are all of the factors of 6. All over the factors of the leading coefficient. Now there is no number written there, so it is a 1. And the factors of 1 are 1 times 1. You don't need to repeat anything, so you just write 1. So take all of these numbers in the top and divide by all of these numbers in the bottom. Now in this case, it's pretty straightforward because all of these numbers divided by positive or negative 1 is just all of those numbers. So the rational root theorem says that if I wanted to find out the roots for this cubic function, I would start with plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6, right? So I'm not going to plug in like 7. I'm not going to plug in negative 4, right? It's telling you, kind of giving you a roadmap of how to move forward. Do the same thing for the next one. Again, start with the constant. It's a 3 or negative 3, so that's pretty straightforward. Only 1 times 3 are my factors. Over, this one actually does have a leading coefficient of 2. The factors of 2 are 1 times 2. Don't forget to always put the plus or minuses. Now this is a little tougher. All right, so remember, you're going to take each of these numbers in the top and divide by each of these numbers in the bottom. So here's how I do it. I focus on the first one, 1 divided by 1 is 1. 3 divided by 1 is 3. So I'm going to write plus or minus 1 and plus or minus 3. Now I'm going to divide by the second number. So 1 over 2, that's 1/2. Don't forget the plus or minus. And then 3 over 2 is 3/2. So these are all of the possible rational roots that I would try to plug in to see if any of them would actually be one of our zeros. Okay, now let's kind of put it into practice. So we're going to find all the possible rational roots or zeros using what we just practiced. And then we're actually going to do it. We're actually going to try to figure out if any of them are going to be a root of this polynomial. All right, so starting with this one here, I have the 4. All right, so plus or minus 1, plus or minus 2, plus or minus 4, right? Those are the factors. I don't need to write 2 of the 2's, right? Over, the leading coefficient is 3, so that's plus or minus 1 and plus or minus 3. So the possible rational roots, I'll write them all out. I always write down the numbers on top first. I don't actually write down anything first before I do that. And then after I divide those, then I'm going to divide by the second number, right, which is going to give me plus or minus 1/3, plus or minus 2/3, and then plus or minus 4/3. Okay, so this is going to be all the numbers that I'm going to try to use when I try to figure out the roots of this polynomial. So I'm going to start with 1. So put 1 in the corner. We're going to use synthetic substitution, which when we find one, essentially is going to turn into synthetic division. So write down the coefficients, 3, 4, -1, 4, and -4. All right, remember, I'm hoping that I get 0 at the end. So 3 times 1 is 3. Add, you get 7. You get 7. That's 6. Multiply times 1, you get 6. That's 10. And we do not get 0. If you don't get 0, you just go to the next one. So I'm going to go to -1. And I'm just going to keep repeating this process until I find one. Okay, it might take a little while. So 3 times -1, -3. That's 1. That's going to be -2. That's 2. Okay, so still no. Let's try +2. Okay, so trying +2. I get 6. That's 10. Uh-oh, we're going the wrong direction here. What was that, 38? Uh-oh. That's going to be 84. Definitely not this one. What is that, 80? Doesn't matter. And then let's try -2. Fingers crossed. We'll finally get one. All right. Bring down the 3. That's -6. It's -2. That's 4. That's 3. It's -6. We got a chance here. Oh my goodness, finally it worked. I love it. So we finally got one. When you get that 0, this number right here is one of your zeros or roots. All right, so when it says to find all of its zeros, we just found one, x equals -2. That is one of our zeros. Okay, now here's what we're going to do. We're going to take those coefficients in the bottom here, and we're going to write, basically, we're going to factor this polynomial. All right. Now this is kind of the tricky part, so make sure you're focused on this. We're going to practice this a lot. It does take a lot of time to figure this out. So how this works is I'm going to write x plus 2. Now you may be thinking, but Mr. Frender, you just found that one of the answers is -2. Why did you change the sign? Remember, when you write things in root form, it's always x minus that root. Okay, so subtracting a negative is really addition. All right. Now for what's remaining, I'm going to go 1 less than this exponent of 4, like we did in our practice with synthetic division. So starting over here with this coefficient, it's 3x cubed minus 2x squared plus 3x and minus 2. Now I'm just going to kind of ignore this x plus 2 factor at the beginning, right? Just kind of ignore this for now. And I'm going to focus on factoring by grouping, if I can, this polynomial with 4 terms. So factoring out, it looks like they both have x squared. That leaves me with 3x minus 2 plus 1 times 3x minus 2. Okay, so keep going. I get x squared plus 1 times 3x minus 2. And now I'm going to bring down the x plus 2. This is as far as I can go in terms of factors for this function. Let me get the correct letter there. Sorry about that. This is a p of x. And I want to remind everyone, I'm going to do this a ton in class, but this polynomial up here and the one that I just found down here, these are the same thing. One is just factored and one is in standard form, okay? So we already found one of these zeros. X plus 2 equals 0. We got x equals -2. That shouldn't surprise you, right? That was our first one. This x squared plus 1, setting that equal to 0, you're going to notice is going to give us 2 complex or imaginary roots, right? Move this over, you get -1. Hopefully you remember when we took the square root of -1, that is actually plus or minus I. And finally, 3x minus 2 equals 0. That's going to be x equals 2/3. So when it says to find all the zeros, both real and imaginary, we ended up having 4 total, which in a moment you'll see should not surprise you, right? The highest exponent is 4. So I'm expecting to see 4 total. I have 2 real ones, right? These x equals -2, x equals 2/3. Those are 2 real roots. And then this one right here, x equals plus or minus I, that gives us 2 imaginary or complex roots, all right? But a total of 4. And that's kind of the whole process. That's, you saw stuff we've done multiple lessons ago and stuff we did the first semester, all wrapped up in this, okay? Okay, let's go to the fundamental theorem of algebra. All this is really stating is that for every polynomial, whatever the degree is, right, like the one we just did had a degree of 4, then you're expecting to see 4 total roots. Okay, now again, they may not all be real, they may all be real, they may all be complex, right? It just doesn't, all you're looking for is that they all add up to that highest degree. So in this case, like I mentioned, the highest exponent was 4, so the degree is 4, which had 4 zeros. Okay, now the conjugate root theorem, I did touch briefly on this in a couple lessons ago, but here it is formally. Essentially, anytime you have an irrational or non-real zero, they come in a pair, all right? So you just change that sign that's in front of it, like we did when we did complex numbers and operations of those with quadratics, okay? That'll hopefully come back to you. So like for this first one in the part A, 3 minus square root of 5, then you also have 3 plus the square root of 5. If this one is positive 2 root 6, you have negative 2 root 6. If this one is positive 12i, then another root is negative 12i. And if this is 7 plus 3i root 2 over 4, you have 7 minus 3i root 2 over 4. Okay? And it does ask to write the corresponding factors, right? Remember, I just touched on this on the last question. It's always x minus that root or factor. So this one's going to look a little bit weird. We can write x minus 3 minus root 5, and then times x minus 3 plus root 5. Feel free if you wanted to make those, distribute the negatives, you could. This one would be a little bit simpler. We have x minus 2 root 6, and then times x plus 2 root 6. Remember, think opposite for the signs. Same thing here, x minus 12i times x plus 12i. And the last one, this will be a little tougher. I'll try to do this vertically. X minus, and I'm going to write 7 plus 3i root 2 over 4, and then times x minus 7 minus 3i root 2 over 4. Key thing here, guys, you're going to see me do this in a moment, is to make sure you put the opposite sign in front. Okay, 2 more, and then we'll be finished. So this one says to factor this cubic polynomial with 4 terms, completely given that the square root of 3 is a 0. So again, that's an irrational number. So if the square root of 3 is a 0, then also the opposite of the square root of 3 is a 0. So thinking about the factors that I just did, we had x minus the square root of 3 times x plus the square root of the 3, thinking opposite, remember? So distributing this, I get x times x, which is going to be x squared. Then if you remember from the work we did with complex conjugates in November, December, you should know that when you multiply conjugates, the middle pieces are going to make 0. I'll show you here. I'll multiply everything out. But when I do this work, I don't do that since I know that makes 0. So x times root 3 is going to be x root 3. Negative root 3 times x is going to be minus x root 3. So you'll see that makes 0. And then minus and this is difficult, root 3 times root 3 is actually just 3. Okay, so those make 0, so this becomes x squared minus 3. All right, now I'm going to figure out the other factors of this by using division. So I'm going to make x squared minus 3 my divisor, and my dividend is x cubed minus 6x squared minus 3x plus 18. So this is just a throwback to long division, just to show you that you can use long division here. So I need to figure out something times x squared that's going to give me x cubed. So that's going to be x, right? X times x squared is x cubed. X times negative 3 is negative 3x. Bring that down. Subtract. All right, and you're going to get the negative 6x squared. That's actually going to be 0, so plus 18. All right, so I need to figure out something times x squared to give me negative 6x squared, which is minus 6. That's negative 6x squared. Negative 6 times negative 3 is plus 18. Subtract, and you get 0. All right, so this right here, my quotient, multiplied by my divisor, gives you the dividend. So fully factored is x squared minus 3 times x minus 6. Now you may have noticed that you could have actually done factoring by grouping at the beginning. That would have also given you the same thing. And I'll talk with Ms. G on how we want to do this. We technically did get to that factor from this, so we may ask you to do x minus the square root of 3 times x plus the square root of 3 using your understanding of the difference of two squares. Just that 3 is not a perfect square, so I'll talk to her about how we want to do that, but ultimately I expect either one of these will be the answer that we'll go with. Okay, last one. I am going to go ahead and just try factoring by grouping. I always try to factor first if I can. So factoring by grouping, I have x squared times x plus 1 in that first group. Factor out of 9, I like x plus 1. So this is x squared plus 9 times x plus 1. We told you guys in the first semester, right, this is fully factored because the sum of two squares is not factorable, all right? But if you wanted to, right, if you wanted to take that x squared plus 9 and set it equal to 0, move the 9 over, take the square root of both sides, you would see that x equals plus or minus 3i. And so you could actually, if you wanted to, break this down a little bit further and write x minus 3i times x plus 3i, and that would get you to the zeros or roots quicker. Anyway, hopefully a lot of this makes sense. If you still have questions, come see me in office hours, and good luck on the homework.